Hello, welcome to the Dr. Neutron Radio Hour. I'll be your host today, Dr. Neutron. Dr. Wisby had some complaints that he wasn't mathematically rigorous enough. So I, Dr. Neutron, will be taking over for you. We had a question from a student about a physics problem. Let's take a look. The problem says a 68 kilogram hiker walks at 5 kilometers per hour up a 4% slope. The indicated incline is the ratio of the vertical distance and the horizontal distance expressed as a percentage. For the steps and strategies involved solving a similar problem, you can view the video tutor solution. So what is the necessary metabolic power? Well, let's assume that you can model her power needs as the sum of the 380 watts of power to walk on level ground plus power needed to raise her body up the appropriate amount. Assume that the efficiency of the body is 25%. All right. Let's take a look. We'll start by drawing our jogger who is going up an inclined plane. And they are really, really jogging. Okay. They are going up this plane, and the problem says that the normal distance is 380 watts of power to walk on level ground. So to go across this distance is 380 watts. Now, let's remember that 1 watt is equal to 1 joule per second. All right. So we need to get the energy that they use. Right? Now, we don't know how far this person walks. We're just going to assume that they're going up an infinite hill. Maybe they're in the mountains in Colorado, and they're going up a 14er. I did it one time, and it's very, very painful. There's our mountain. They're walking up here. It's a long, long ways. We don't know a distance, and we don't know a time, but we'll just make one up. It doesn't really matter. And we'll say the time that they walk is 1 hour, right? We'll say T equals 1 hour because we've already got this in, well, this is 380 watts, but we are given a velocity. So V equals 5.0 kilometers per hour. That is their distance this way. Well, if we set a time, then we can find a distance. Okay, so we're going to need to get the height that they go up here. So some height here, right? And we're going to need to get the distance that they travel. All right, let's talk about the energy that they need to go up this hill. that energy is given by U equals mg times h. Or we'll say this is delta y. Okay, so we'll rewrite this as mg times delta y. Now, since they are a human is 25% efficient, that means they're going to need 4 times that amount of energy. So for this is the work it takes to increase the potential energy, and we need that's 25% of the total energy. So we can divide this by our to get our total E, we'll divide U by 0.25, which is the same thing as multiplying 4 times U, or we'll have 4 times mg times delta y. Now, we want to get this in terms of power. So power is energy that we use divided by time. So they're going to increase this potential energy during some time period. We'll call that delta t, which is time it takes to ascend. The hardest part about this problem is figuring out what the problem is telling you. They worded it in a very tricky way so that you have to think about what they're saying. So I think the hardest part about this problem is figuring out what the problem is asking for. Okay, so then we could say that their metabolic power, so their power for ascent, ascent power is equal to 4 times mg times delta y divided by delta t. So this is the total energy that it took to increase the potential energy, or sorry, this is the metabolic energy it took to go up that hill. And if we divide by the time period, that gives us power because this all has units of joules per second. This bracket means what are the units of this, which is joules or seconds or watts. So this is the correct formula for uh, to find the power to go up the hill. Now we need to add that to what we're given in the problem because we're given in the problem that to walk that distance is going to take 380 watts. So if they walk during the same distance, it's going to be 380 watts. So that's going to be our total power is the power it would take to walk in flat ground plus 4 times mg times delta y times delta t. Now, you might say, but Dr. Wisby, we don't know the time and we don't know the height. So what are we doing here? Why are we even doing this? Well, we do know the velocity. We know the velocity that they're traveling on the hypotenuse of the triangle. It tells us in the problem that the velocity is 5 kilometers per hour up the slope. That's a clue. Now, delta y, if we take delta y, our change in height, and we divide it by delta t, well, this is going to give us our delta, our velocity in the y direction. All right. You see where I'm going with this? We know our we know our velocity this way. What we don't know is our v, our y velocity. But the all right. So this is my energy. Now, delta y over delta t equals my y velocity. So delta t here, this is going to equal delta vy. So that is my component of velocity in this direction here. Now I know what their velocity is this way. So now we've got a, a triangle. So this is the hypotenuse of my velocity triangle. And what I'm after is this side over here. Now, how do you get the angle? Okay, because it says it gives us the angle in a percentage, which means it says that there's a slope of 4%. So our hill has a 4% slope, which is used in architecture sometimes, depending on their application. But that means the ratio of y to x is 4% or 0.04. Okay? So that it doesn't matter how far they go in y and how far they go in x, the ratio of those two equals 0.04. So we want to get that into an angle, right? And we know that this is also equal to tangent of some angle theta here. Okay, so our ratio equals 0.4, which should equal tangent of theta because tangent of theta equals y over x. Okay, so now what we do is to find our angle, we take theta is equal to the arctangent of 0.04%. So the hardest part about this problem is just figuring out what the heck they're talking about because it's kind of confusing, but that's okay. All right. So now we have, all right, we need to get we know our angle here. So we have, we need to get Vy and we have our hypotenuse. So in our velocity here, the hypotenuse is 5 kilometers per second. So then Vy, which is what we're after, equals V times sine of theta. We know what theta is now. We can plug it in here because actually for small angles, sine and um, sine and tangent are equal for very small angles, but that's okay. We're going to actually compute the angle and then we'll put it in and do it the hard way. Okay, so actually, if we calculate arctangent of 0.04, then we get an answer of, we end up with 2.3 degrees. Okay, that's what we get. But actually, we know that tangent here is, it's equal to sine of theta for small angles, sine of theta. So we don't even need to change that because we have tangent of theta equals 0.4, sine of theta equals 0.3, but we'll put in the angle just because, right? So now we're going to go back up here. We've got our expression here. This is our total power. And now we just need to say delta y over delta t equals delta Vy. So this is going to give us P is going to equal 380 watts. That's just from walking whatever distance this is, plus 4 times mg times delta. I thought I wasn't recording. Delta Vy. Okay, now we're going to put this in. So we'll have 380 watts plus 4 times mg times v sine of our angle there, 2.3. If your calculators in degrees, that's what you're going to want to put in. And so now we'll plug in our numbers. We'll see what we get. All right, 380 watts plus 4 times their mass. What was the mass? I can remember. 68 kilograms. Seems like a lot of people weigh 68 kilograms in this book. Just an observation. Times velocity, 5 kilometers per hour. Not helpful. Slightly helpful. Times sine of 2.3 degrees. Right there it is. But this is not in meters per second. So we we're going to have to convert that to get the right number. We can't leave that in kilometers per hour. We have to convert it into meters per second. So we have to add the correct conversion units. We want to get seconds. Okay. So to convert from hours, we say, okay, 1 hour has 3,600 seconds. Okay. That's going to, our hours are going to go away. This is the number of seconds in an hour. Now we need to get rid of kilometers. So we're gonna say that 1 kilometer is there's 1,000 meters per 1 kilometer. Our kilometers will cancel. We'll be in meters now, and we're gonna get rid of the hours. Okay, and so it's gonna give us the right answer. So now, the moment of truth. Switch over to Mathematica, and we're gonna start typing it in. Yes, we'll put it in there, folks. Oh yeah, watch me type it. 380. That's not big enough. Who can see that? 380 watts plus 4 times 68 kilograms times 9.8 meters per second squared times 5 kilometers per hour times we've got a sign there, okay, and it needs to be in radians. So we're going to say sine of 2.3, that's in degrees, so it'll be times pi divided by 180. Why do I always do it in radians? Honestly, because I don't know how to put Mathematica in degrees, and I just like, I've done it so much, I like radians now. I don't know. So 1 hour per 3,600 seconds times 1,000 meters. Ooh, there it is. Divided by 1 kilometer. Is it going to cancel? I think it will. So we're going to get something that's wrong. That was not the right answer. But that's okay. We're going to figure out what happened. On second thoughts, I think it could be the right answer. We got these funky units. Some of our units, well, should have canceled. But that's okay. We have kilograms, meters, squared per second. Something did not cancel. We got an extra meters in there. That's okay. Actually, that's right. So if we change all of this mess to W, because, well, it is watts, we get 528 watts or 530 watts. Well, folks, it looks like we've done it. That's the right answer. But actually, we could have just multiplied by that percentage, by the incline, okay? We didn't have to use sine there. We didn't have to do it the hard way, but we did. If there's one thing I'm good at, it's doing the hard way. Have a great night. I'll see you tomorrow. Sleep well.
Thank you, like and subscribe down below.